Okay, so let's recap what we learned last semester about the fatigue test. Okay, the fatigue failure criteria. So suppose a component is subjecting to a cyclic loading, uh, so we can uh, detect this. It's the maximum stress and the minimum stress, and the mean stress and the reversible stress. Right? So this is the experiment for the fatigue test. So I'm gonna skip this. So I think you guys must be familiar with that, right? So if we already know it's the maximum stress, and then we can convert it to the maximum stress, right? Maximum stress, right? So similarly, we can get its minimum stress, right? And this cyclic loading, we're just repeating periodically, right? Therefore, we can figure out its mean stress, or we can say it's the mid-range stress, sigma m equals to the maximum stress plus the minimum stress divided by 2, right? And the amplitude stress, or say the stress amplitude, sigma a, equals to the absolute value of the difference between the max and minimum stresses divided by 2, okay? Okay, so if the mean stress or mean range stress equals to 0, okay, if the mean stress or the mid-range stress equals to 0, and we can use the SN diagram to figure out what is the fatigue, to figure out what is the endurance limit, right? Okay, so if we just look back to the fastener or the bolt component, okay, by using this cyclic stress concept. Okay, so we have the minimum force, the bolt, the B here represent the bolt. Okay, the minimum force of the bolt equals to the C times the minimum external force plus the Fi, which is the initial force, right? Initial force. And the FB max is the maximum force of the boat. Okay. Okay, equals to C times the maximum external force plus the initial force. Okay, initial force. So we can figure out what is it's the stresses is first is the alternating sigma A, right? Alternating stresses, right? So we'll just divide it by, or just divide these stresses by this AT, which is the tensile stress area, right? Tensile stress area. Okay, so we can get sigma A, right? Equals to the maximum stress minus the minimum stress divided by 2. Okay. Okay. So we can use this equation to this fasten whose mean stress, whose alternating amplitude stress. Okay. Okay, so we got the sigma A of the fastener or the bolt for the fatigue. Okay, so we can just rearrange this equation. Okay, so we can eliminate this Fi. So we can get the sigma A, the alternating stress. Right? Similarly, we can figure out what is the maximum stresses. Right? Oh, sorry. We can get the mean stresses. Okay, what is the mean stresses of the boat? Okay, so we get two key variables here. Okay, one is the alternating stress and the mid-range stress or the mean stress. So these two stresses are the key factors for the fatigue analysis. Okay, fatigue analysis. Okay, okay. So for this when the sigma m, the mean stress, equals to 0. I already mentioned this previously, right? So if the sigma m equals to 0, okay, that's mean we can get a completely reverse stress. And in this case, we can use the SN diagram that we already learned, right? Last semester, okay? So if the sigma m or the SM, the same thing, okay? So we can use the SN diagram to figure out what is SE is, which represents the endurance limit, right? The endurance limit. So for the SN diagram, it's only for completely reverse stresses, which means the sigma A equals to 0 and without preload. Okay. Okay, so if the case is that if the sigma m not equals to 0, okay, so we have to use these failure criteria, such like the Guman, Gerber, SME, ellipse, and so on. Okay. Okay. So we can plot this SA and SN diagram for those sigma m not equals to 0. Okay. And we can mapping this SN diagram to this SA and SM diagram that is representing at this y-axis, right? Which means the sigma m equals to 0, right? So the y-axis represents the sigma m equals to 0. Okay, so we can figure out what is its endurance limit is right here, right? And we can figure out what is the sigma A is corresponding to the different cycle number, right? Here and here, right? Okay, so for this number of cycle approach to infinity, that's mean the number of cycle is greater than the 10 to 6. Okay, 10 to 6. Okay. Okay, so suppose we can use the fatigue criteria, the Guman, right? So for this line, it's known as the Guman diagram, which is linear fitting. Okay, so the Guman diagram, which can be defines the induced limit as a function of mean stress. Okay, the endurance limit SE as a function of the mean stress sigma n. Okay, so in the y-axis is the sigma A divided by SE, endurance limit. In the y-axis is represented SM divided by SUT. Okay, so the Grumman diagram that's shows the drop in the SE for racing in tensile SN. Okay. Okay, so for the Grumman, for the criteria fatigue failure with the sigma m, which is not equals to 0. Sorry. So for this sigma m, which is not equals to 0. Okay, so let me see what's the problem is of this screen. Okay. Okay. So we can evaluate this right. So we can figure out this two line with the intercept Okay, so we can figure out what's the intercept of the loading line and the Schumann equation. Okay, so for example, this is the loading line, right? For the fastener, we have the initial stress, which equals to the Fi divided by the tensile stress area, right? So when this boat is subjecting to the fatigue or the cyclic loading, right? So then we are representing the sigma m and the sigma a, right, during this cyclic loading, right? So we can get the different values of the sigma a and the sigma m here, right? So we can get the loading line of this boat. Okay, so we already know the Goodman fatigue, right? The Goodman fatigue criteria representing the linear line, right? Representing the linear line. So we already know that, right? Okay, so we already know that, right? So this is the linear for this Goodman. Okay, it's a linear for this Goodman. Okay, it's a linear for the Goodman. Okay, therefore we can find the equation of the Goodman criteria, right? So for the Goodman criteria for infinite, for the finite life, okay, for the finite life, that's mean the number of the failure is less than infinity. We can say it's the number of the cycle is less than 10 to the power of 6. Okay, and we can use the equation like this. Okay, and in the case if the number of cycle reaches infinity, that's mean the number of cycles is above the 10 to the power of 6. So we can use the Goodman criteria for infinite life. Therefore, we can use these two equations to representing the number of cycle reach infinity. That's mean we got its endurance limit, right? So we have this equation for the Goodman criteria, right? And also we have this loading line as I already mentioned previously. So we can find the solution, the intercept of these two linear equation, right? Okay, find the intercept here. So the typical load line starting from the constant preload that increase with a constant slope. So it creating two SA equations solving for the SM and substitute into the Goodman equation. Okay, so we have the loading line equation of the Goodman equation, and we can figure out what is the intercept of its alternating stresses, right? We can get what is the alternating stresses, SA and the SM at point D here, right? Okay, so and then we can just figure what is the fatigue safety vector is based on the Goodman and the constant preload line. So the safety vector equals to the SA, the alternating stress divided by the sigma A. Okay, and the SA that we already get, right? We already get the SA. Where? Here, right? We find the intercept. Okay, you know what I'm saying? So it's similarly like what we already learned in the last semester, the ratio between, right? These two SA and the sigma A, right? The SA, right? And the sigma A, right? Right. So for similar, you can get this safety vector, which is the ratio between AC and AB sections, right? Okay. So we got its safety vector. Okay, and we just plug this SA, the intercept, right? The solution between the loading line equation and the Goodman equation, right? We just plug this in here, and then we can solve its safety vector based on the Goodman criteria. Okay, and similarly, other failure curve can be used. Okay, following the same approach, solving SA, SM, and finally we got the safety vector. Okay. Okay. So repeat load spatial case, the boats joint over experience repeating load where external load fluctuates between 0 and the maximum external force. And if we set in the minimum external force equals to 0, okay. Okay, so the minimum equals to 0 and the minimum equals to 0 and the minimum force equals to 0, okay. So we can get the sigma A, the alternating stress, and the mean stress. Okay, so for this case, we're just discussing the fluctuating stresses or the force between the 0 and the Pmax. Okay, therefore, the constant preload line will equals to the sigma M equals to the sigma A plus the sigma I, right? The pre-stress. Okay, and load line has a slope of unity for repeating load case. Okay, repeating load case. Okay, and the intercept load line equation with the failure curves to get the intercept SA and dividing the SA by the sigma A to get the fatigue safety vector for repeat load case for each failure curve. Okay, so if we're looking into a summary of those fatigue criteria and load line, right? So we got load line, which is the repeating force between 0 and the Pmax, right? So we can solve the intercept or the solution between the load line and the Goodman. And also we can find a solution of between the load line and the Gerber. Similarly, you can get the intercept of the load line and SM ellipse, right? So just based on the different failure criteria. Okay. Okay, so this is what we just a summary. Okay, so I just get one slide to show you the different curves corresponding to the different failure criteria. Okay, so of the Goodman, Saltberg, Gerber, SME, and so on. Right. So this is our load line. Right. So we can figure out the intercept with the different failure criteria to figure out what is the solution is here, the intercept here, right? Low line with the this line should be the Gerber, right? And this intercept, which is the SME ellipse, and this line, right? Is the linear static yielding, right? So you can figure out sorry, this line is this intercept is for the Goodman, and this line is for the linear static yielding. Okay, so the various criteria of failure, right? So we can find these intercepted solutions between those failure criteria and the load line. Okay. Okay, so this is the brief summary here. So we can find this safety vector from Goodman, okay, the safety vector from Gerber, and the safety vector from the SME ellipse. Okay. Okay, so for convenience, the sigma A and the sigma I can be substituted into any of the fatigue safety vector equation. Okay, doing so for Goodman, right? We get the safety vector, right, from Goodman and low line. And if there's no preload, C equals to 1, Fi equals to 0 and resulting the NF naught, right, equals to this term from the Goodman criteria, okay, from the Goodman criteria, okay. So preload is beneficial for resistant fatigue when this ratio NF over NF naught is greater than unity. This puts an upper bound on the preload. Okay, so we have to define what's the upper bound of the preload is, which have to match the relation of the Fi has to be smaller than 1 minus C times the SUT times the tensile stress area. Okay. Okay. The yield check with fatigue stress. As always, static yielding must be checked. Okay, so if the static force, even the cases is in fatigue loading, we still have to check its yielding static. Sorry, yielding, yes, the static force, whether this force will causes yielding, right? So if this stresses already causes this boat yielding, so we don't have to take any fatigue criteria into account, right? It's not necessary because only for this static loading can induce the plastic deformation, right? So in fatigue loading situation, since the sigma A and sigma N are already calculated, it might be convenient to check the yielding with the MP, okay, equals to the SP, the proof strength, okay, the proof strength divided by the sigma A plus sigma N. Okay, sigma A plus sigma N. So this equivalent to the yielding vector of safety MP, okay, MP equals to the sigma P, sorry, the SP, which is the proof strength divided by the sigma B, okay, the sigma B. Okay, so just plug these values here, this equation here, so we get this yielding factor of safety equals SP times the AT divided by CP plus FI. Okay, so the last section we're gonna briefly discuss what's the failure scenario is for this joint, bolt, and nuts or fastener is. Okay, so there are different cases for this situation A, which is the joint, right, in shear, right? We have the joint with the nuts, sorry, with the bolts, right? So we just fasten to fix two members, two plates. Okay, and what type of the failure or what type of the failure scenarios is for the shear applied to the joint. So the figure B shows the bending, right? The bending of the bolt or the member. And the figure C shows the shear, right? It's a shear to tear this bolt out. Okay, and for the D, which is the tensile failure of the member. Okay, this plate already broken parts, okay, broken parts. And for the figure E, representing the bearing stresses on both or the member, right? So it's already deformed. Okay, and for the F, represents the shear tear out the members. Okay, and for the figure G, represents the tensile tear out. Okay, the tensile tear out. So one member already broken. Okay, already broken. Okay, so for the bending moment, it's approximately that we can just approximately get the moment equals to Ft over 2. The T where's the grip length. Okay, the grip length. Okay, i.e. the total thickness of the connecting parts, and the bending stress is determined by the regular mechanics of the materials approach. So it's the S, the I over C is for the weakness number or for the bolt, right? Okay, for the bolt. So the sigma is the normal stresses from the bending, okay, from the bending, and C is the distance from the neutral axis to the surface, okay, to the surface. Okay, so for shear, simple direct shear, right? So if we have the preload, we have the pre-stress or preload, right? If we have pre-stress or preload applied to the bolt, and this pre-stress or preload, when these tiers apply, this pre-stress and preload can be regarded as the resistance because they're as the friction, right? So this preload create the shear stress in between the two members. Okay, and this friction force between these two members can be regarded as the resistance to the tier or the shear force. Okay, the shear force. Okay. Okay, so for bolts, determine whether it should cross the nominal area or the cross threaded area. You can use the area based on nominal diameter or the minor diameter as approximates. So in the case if it fail, if this friction induced from the preload cannot resist to the shear, so will be tear out, the member tear out. Okay, the member tear out. Okay, the member tear out. Okay, so this is the case what we already know, right? The simple tension fail. Okay, so okay, so this plate is be broken apart. Okay, be broken apart. Okay, so use the smallest net area of the member with holes removed. Okay, the area here. Okay, and most of the cases occur in this situation is that the bearing joint. Okay, what is the bearing joint? It's designed with little or no preload. Okay, so if your preload is not enough, or there's no preload, well, it's have the highly possible to cause this tensile fail. Okay, for this tensile fail. Okay. Okay. So failure by crashing known as the bearing stress. So bolt or member with the lowest strength will crash first. Okay. It is bolt or member with the lowest strength will crash first. Okay, load distribution on cylindrical surface is non-trivial. Okay, customary to assume uniform distribution over projected contact area. Okay, so we have to say the load distribution on the cylindrical surface is non-trivial and customary to assume the uniform distribution over the project contact area A equals to the T, the thickness of the members times the diameter, okay? And the thickness is the thinnest plates, okay? And the D is the bolt diameter, okay? Okay. Okay, so for the bearing joint, it's designed with the ladle and or with no preload. Okay, so there are two failure cases could occur. One is for this bearing joint. Okay, for this bearing joint, that's mean no preload or with a little preload. One could be the tensile fail. Okay, the tensile fail. Okay, and it could be fail the crash. The crashing. That's mean, well, this plate is not broken, but it's certainly deformed. Okay, it's certainly deformed. Okay. Okay, and the cases, the other case for the failure is called the shear out or tear out. Okay, the edge shear out or tear out is avoided by spacing both at least 1.5 diameter away from the edge. Okay. Okay, so if this edge, or this edge, okay, this distance has to be 1.5 diameter from the edge. Okay, from the edge. Okay, if not, this tear out or shear out could happen. Could happen. Okay, so shear stresses is beyond the shear strength of the materials. That means the materials directly fail. Okay, so it's this case. Okay, so if the shear stresses is already beyond its materials property shear strength, of course the materials will directly fail. Okay, so in this case, this plate whose shear stress is smaller than the shear stress applied, right? So this member fail first, and this case is that the bolt whose shear strength is smaller than the shear stress applied. That means the bolts fail first. Okay, fail first. Okay. Okay, so if we deal within the shear joint, okay, shear joint with eccentric loads, we have to find its centroid. Okay, I think you guys already know how to figure out where's the centroid is, right? By your statics course. Okay, I'm not gonna repeat those processes again here, so you guys have already learned it, right? Previously. Okay, so this case is that if that for this shear joint with the eccentric load. Okay, so in this case is that if we have a beam, right, with two joints here and here, and each joint with four bolts and nuts. Okay, four bolts and nuts. Okay, so the resultant force on the pin with a net force and the moment. The resultant forces on the pins with a net force and moment are the primary shear and the secondary shear. The primary shear is from the direct load for the V1, which is shear force. Okay, it's the shear force. If we look in the previous, we have the V1 here, right? If there's a beam, right, with the distributed load at the center, so we have the shear force V1 and V2 apply at the two end, the two boundary, right? The two boundaries O here. Okay. So the F prime equals to V1 divided by N. N is the number of the bolts. How many pins here? Okay, so if we just look into one joint here, one joint here, one joint here, right? One joint here. So there are 4 pins. Okay, there are 4 pins. Okay. So the F prime equals to the V1 divided by 4. Okay. And the secondary shear due to the moment load around the centroid. Okay. So of course the centroid's locations here, right? Because it's a symmetric, right? Symmetric. So if we regard this force, right? So you have two resultant V1 and V2, right? So if we only look at one end here, so when we move this force here, there must be a moment, right? There must be the moment. Okay. So except for this F prime, We have to consider the secondary shear force, right? The secondary shear due to the moment, right? Secondary shear, F double prime, right? So the moment applied to the joint, the pin A, and A equals to the F A double prime times the RA, right? So if we only look into one joint here, is composed of this FA prime, right? It's from the direct shear. And a moment equals to the RA cross the FA double prime. Similarly, for the pin B, C, and D. Okay. Okay, so there we get FA, F1. Okay, F1 equals to the FA double prime times the RA times the FB double prime RB and so on. And you will get the FN double prime times the RN. Okay. Okay, so in this case, the FA double prime over RA equals to FB double prime over RB equals to FC double prime over RC. Okay, over RC. Okay, and then we can solve these two equations to get the Fn double prime here equals to this term. Okay. Okay. So if the diameter of the H bolt is assumed equal for this case, if not, one replace F double prime with shear stress. Okay, with shear stress. Okay, and this shear stress double prime so equal to 4 times the F double prime divided by the pi d square. Okay, divided by pi d square. Okay. Any questions? Okay, I'm gonna skip these examples. I think you guys can just work on this as your assignment. Okay, so assignment. So this course will be ended here. This course of the fastening joint, fastening screw will end here. Okay, so next we're gonna look into the other mechanical component, spring. Okay, spring.